Hello, so, special relativity. Last week we looked at the concepts, the processes, the ideas behind it. Today we're going to look at how we describe that mathematically, and it will be much simpler. Because it's such a hard concept, the questions are generally quite straightforward. So, electron is travelling fast, here's its mass, here's its speed. It wants to know the increase in mass that occurs when an electron accelerates from rest to that speed. So let's pick our equation. We've gone with m equals rest mass, m naught, rest mass, divided by gamma, by our relativity factor. So we've got 9.11 times 10 to the minus 1 divided by all square rooted 1 minus b squared over c squared. Our velocity is 4 times 10 to the 7, and our speed is of course the speed of light. This is more true than any other topic or any other type of question, one step at a time. You've got powers, you've got squares, you've got divides, you've got minuses, you've got square roots. If you put it in a calculator and just randomly press equals, you will get it wrong, one step at a time. So 4 times 10 to the 7 squared, 1.6 times 10 to the 15, 3 times 10 to the 8 squared is 9 times 10 to the 16. Next step. Let's divide those numbers by each other. So we've got square root of 1 minus 0.0177 recurring. So let's do 1 minus that. So we've got the square root of 0.982 recurring. Let's take the square root of that. So, the factor by which it changes is 0.9910712498. Normally we do one or two significant figures. It's more important that we include all our decimal places here, because with relativistic changes it's often our 4th or 5th decimal place that makes the difference. Whether you're travelling at 1 metre per second or 4 times 10 to the 7 metres per second, these first two numbers are always going to be 99. It's always going to be 99. It's the 3rd, 4th and 5th decimal places that makes a difference here. So that's the amount it will change by. So let's figure out our relativistic mass. So we've got 9.11 divided by 0.9910712498. So our relativistic mass and it's a tiny increase. We've gone from 9.11 to 9.19 times 10 to the minus 31. Do we stop there? No. We look back at the question, mass increase. We were 9.11, now we're 9.19. So let's minus the rest mass. And we've got 8.2 times 10 to the minus 33 kilograms. That's the increase in mass. And it is so negligible. It's 100th of the mass of the electron. You can tell that from here, we're in the 1% region. But when we're looking at masses in particle accelerators, well that's night and day, that difference, we've got to use it. that's an example of an exam question. I gave you one to do for homework that I said I'd go over, and that's what we're just going to do now. So, what's really important is that we can get this question down just in black and white. Well, I say black and white, I'm in black and yellow. So, your question had 2 particle detectors. They were 34 metres apart. And it wanted to know, first of all, how long the light would take from the reference frame of the particle accelerators. And it doesn't get more simple than distance, that time equals speed over distance. Having said it doesn't get more simple, let's take a moment to think about this. Time equals distance over speed. So we've got 34 metres, it's light, so 34 over 3 times 10 to the 8. Just about to make a mistake. I've not read the question properly. It's not light that's travelling, it was a particle travelling at 0.95 the speed of light. So let's do that sum first. So we've got 3 times 10 to the 8 times 0.95, and that gives us 2.85 times 10 to the 8. So that gives us a time of 1.19 times 10 to the 7 seconds. That's how long the particles appear to take from the stationary frame of reference of the particle accelerator. Second thing we need to do, part B, is it wants to prove that 75% have decayed and only 25% arrive there. Now it says the half-life is 18 nanoseconds, so within that time we've got 18 times 10 to the 9 going into this number. We've got multiple half-lives. So based on that number, we should be getting like 1 or 2% coming through to the other side. But the question wants us to prove 25% come through. So we need to look at it and think, well, it's travelling close to the speed of light, so the time the particle experiences will be dilated. So we need to do something with t equals t0 over root 1 minus v squared over c squared. First of all, let's figure out, well, t0, what time are we going to look at? Are we going to look at this time? No, why would we? Let's figure out what the dilated half-life is. So let's have 18 times 10 to the minus 9. Our V is 0.95. Our C is 1. So this time, because they're both times 10 to the 8, I'm dropping the times 10 to the 8 because it just cancels out. So let's work out the 0.95 squared over 1 squared. That should give us 0.9025. So let's do that sum. And that should give us 0.0975. Let's square root that. And it should give us 0.312249899. And again, I'm putting all the decimal places on because it's this 4, 5th and 6th one that matters. So 18 times 10 to the 9 over that number gives us a dilated half-life of 5.7 times 10 to the minus 8. So the particle, as far as it's concerned, it's still got that long to live. It's still got a half-life of 18 nanoseconds. But our observation of that time is longer, so we would see the half-life to be 5.7 times 10 to the minus 8 seconds. So that'll be one half-life, 50% would decay. Two half-lives would be looking at 1.15 times 10 to the minus 7, in which case half again, 75% would have decayed, 25 would arrive, and we can see the time for two of the dilated half-lives is roughly the same as how long it would take. There's only been two special relativity questions that have come up since the specification changed, and they are both identical to the first one we did. The concept is mind-bogglingly hard. You don't need to do anything more than figuring out what it is that's dilating, deciding what's your stationary frame of reference, and then not being an idiot when it comes to pushing numbers on your calculator. A special relativity question really should be easy marks. So there's not a lot for you to do over half term. If you could arrive on Tuesday and bring your entire folder in order. And I'm not just saying that we need to do it. So arrive on Tuesday, your entire folder in order. Repeated myself there, clearly I mean it. Have an excellent break, and I'll see you soon. Bye bye.